My name is Peter Alvaro, and the talk I'm going to give today is called Orchestrated Chaos. It's some of my problems I've identified, solutions I've been sort of kicking around in my brain related to resilience and fault tolerance for giant scale systems. And I'm going to begin with just a little bit about me. Many of you may be familiar with the legend of Persephone and Hades. Persephone, for me, is one of the most interesting characters in Greek mythology because unlike anyone else in the pantheon, she really spends her life in two different worlds and understands a little bit, but not all, about both worlds. A world of light and beauty and music, and a world of darkness and torment. And for those of you who don't know the myth, I'll just give it a real quick gloss. Hades kidnapped Persephone, Hades is the god of the underworld, and took her below ground. Almost immediately, the Olympian gods began rallying, trying to figure out how to save her, and it wasn't long before they did save her. But while she was down there, she got a little hungry, and she helped herself to 6 pomegranate seeds. And as a consequence of doing this, she entered into an implicit contract with the underworld. For the rest of her days, which were many, she had to spend 6 months of every year below ground in that world of darkness and torment, and 6 months, in the world of light. And so, like Persephone, I come from a world of light and beauty and music, the ivory towers of academia, right? I spent about 7 years in the literal ivory tower of Berkeley, and I spent my last year, and hopefully many future years if I'm lucky and I have a good tenure committee, in the redwood towers of Santa Cruz. But during one of my sojourns in industry, I got hungry and helped myself to the perks. I helped myself to 3 stroopwafels and 3 cans of LaCrosse spring water. And as a consequence of this misstep, I entered into an implicit contract to spend 9 months of every year in the world of light and music, and 3 months of every year in a world of darkness and torment, what we call industry. And I think this gives me, I'd hesitate to say a unique perspective, but an unusual perspective on the interaction between these two communities that are struggling really hard to solve very similar problems via different means, 2 communities that have not done a very good job historically of collaborating despite the rich opportunities. So I'll talk a little bit about those opportunities at the end of this talk. But for now, this is a keynote talk, so if you'll indulge me, I'd like to speak in platitudes for a moment. Many of you may have heard or read on many blog posts and tweets and so on that the labor of software engineering and software architecture is principally a labor of managing complexity. And like most platitudes, this is obviously true, but the fact that it's true isn't very helpful, right? I mean, all human labor is managing complexity. The world is very complex, but nowhere is it so sort of stark as in software engineering, where the complexity is all of our own doing, right? We're just sort of cleaning up our own messes. And I think if we dig in and kind of unpack the idea of managing complexity, we think about it for a moment, it occurs to us that we're really talking about 2 very different activities at 2 very different levels of hardness. And the first one is one that we understand very well. Sometimes there's unnecessary complexity, and a good software engineer knows how to remove it, right? There might be unnecessary, for example, redundancy of code or of data. And so, we have this rough-hewn stone, and we open up our toolbox, and our toolbox might include things like functional abstraction and refactoring to deal with unnecessary complexity of code. We might use deduplication and normalization to deal with unnecessary redundancy of data, but essentially these are chisels, and we take out our chisels and we hack away at the stone, and as we do so, as we delete unnecessary complexity, what we might call the essential complexity of the software artifact begins to emerge, right? And at some point, maybe we never get there, but let's be charitable to ourselves and say that we do. At some point we get to a point where there just isn't any more unnecessary complexity to remove. All we have is the essential complexity of the artifact. And now we begin a completely different game of managing complexity, a zero-sum game involving, moving the complexity around, decomposing and recomposing our software artifacts in an attempt to push that complexity to a part of the system where we think it'll be more manageable, right? If I can speak in platitudes again one last time, the second game of managing complexity is a matter of navigating trade-offs, right? Trade-offs. And more often than not, this boils down to navigating a one-dimensional trade-off between productivity and purity, right? Ease of use or convenience and correctness. And 99 out of 100 times, which way do you think we're going to slide this slider? This has been a hard-learned lesson for me, but productivity over purity, right? Let me give some examples in the context of some vignettes from my own life. So I've been teaching about containers for some time, but I just recently taught myself Docker. It was really cool. I had to because I was having students submit things in Docker, and I want to make sure that the submission process works correctly, so I implemented the projects myself and rolled up my sleeves, figured out how to use the tool, and man, is Docker cool, huh? The process of building and shipping software, at least for a sloppy, sort of careless academic coder like myself, used to proceed in 3 phases. Phase 1 went like, convince yourself that it can be done, build a prototype, get it to work on my laptop, by hook or by crook, over-install the necessary dependencies, hack around, try different things in config files, maybe even mess around with my file system, get a scaffolding that just gets that thing to work with popsicle sticks and bubble gum and duct tape and kite string, and then once you get to the end of that phase, you can convince yourself that it's possible. You've got your prototype done. Incidentally, if what you're doing is academic code, at the end of stage 1, you're done, right? For those of you who don't know, academic code, technically speaking, is code that ran on some grad student's laptop at some time. But if you get to that point and you're not just writing a paper, you want to ship code, then you go to stage 2, which is a boring and onerous stage where you make that build process portable. You get the minimal set of dependencies. You get exactly the config entries you want, right? You write some documentation maybe, or at least a README, a build script, and then you try building it in different environments. And this pain in the butt of a process, even for a lazy coder like myself, enforces a certain lower bound on software quality, right? And then stage 3 is you ship it. So I taught myself Docker, and I realized very quickly, oh my God, when you get to the end of stage 1, if you're using Docker, stage 2 is ship. Like if I can get that thing working somehow on my laptop, I can go deploy it in the cloud at scale. So the first thought is, wow, this is amazing. I've never been so productive. It's never been so easy to ship code. But then following quickly on behind that thought is, oh man, like it's never been so easy to ship shit. Like this has got to have dire consequences for software quality in the future, right? Now, did I stop using Docker? Hell no. I never want to go through those onerous, repetitive tasks of stage 2 again. I'm bounding into the future, choosing productivity over purity. A very long time ago, before I was a grad student, before I was even a software engineer, I was a DBA at a company called Ask Jeeves. DBAs are kind of a dying breed. I was just reading an article the other day that said they're one of the last priesthoods of IT, kind of like that. And so if some of you may not know a DBA, if you don't know a DBA, the main role of a DBA is to be a gatekeeper. People want to release features and they want to log them, and the job of the DBA is to say, whoa, ho, slow down, turbo. You need to open a ticket for that. That takes 6 weeks. And there's a reason for this, right? You have to do size estimation. You have to make sure that your schema upgrades can be performed in a rolling fashion. You do the schema upgrade in dev, and then you do it in staging, and then you do it in production, and by the time it's deployed, the site engineers don't care anymore. They're on to the next set of features, right? And so at one point, when I was at Ask.com, I became the darling of the site engineers and the sworn enemy of all the other DBAs. I implemented what I called at the time, now this is pre-NoSQL, right? But what I called at the time the extensible schema that allowed engineers to log not just flat key value pairs, but a sort of arbitrarily nested data structures in a way that they didn't need to change the schema ahead of time. So the site engineers were delighted. Now obviously, because we couldn't do size estimation, because we didn't know what the hell they were logging, we had a really short truncation window on these tables. They were about 2 weeks. And it was very easy to put things in the database, but when it came time to retrieve things from the database, the site engineers had to craft and execute a quite complicated SQL query that denormalized the data and reconstructed their data structure. But neither of these things were problems because 95 out of 100 times, nobody ever went back and looked at the data that they had logged, right? They were on to the next feature. It was just logging was a requirement, they checked the box, they moved on. And in fact, had this all happened like 5 years later, I probably would have just put the data in Mongo. It would have been lost almost immediately, and no one would have known the difference. I kid. Mongo's a great company, and I really look forward to working with Mongo in the future on resiliency, okay? But the point is, productivity over purity, always. And this was a hard-won lesson for me because I'm a purist. I spent the better part of my PhD with my colleagues inventing and attempting to sell these really just beautiful languages that make it easier to program and reason about distributed systems by raising the level of abstraction and focusing the programmer's attention on data and data movement rather than computation, and providing the program with really powerful static analysis tools that allow them to determine when programs can have non-deterministic effects that can lead to data corruption. Unfortunately, nobody bought my languages. I mean, nobody. Like, here's a stat. 5 years after the Bloom language was released, there were about 10 authors of implementations of the Bloom language and about 2 authors of non-trivial distributed code in Bloom. So I reached the wrong audience. Like, the language geeks were like, oh boy, But the infrastructure programmers didn't care at all. Why? Well, one answer to that is Bloom didn't add any obvious immediate productivity benefits to anybody's life. Bloom challenged you to think about your applications differently. And in return, all it gave you was correctness. So that didn't work. Productivity over purity, okay? And by way of dovetailing into the meat of the talk, can we talk about microservices for a minute? Microservices are really popular, and they're only becoming more popular and more widespread. And the reason, right? The reason is the purity of the model, right? Because they're based on the Unix philosophy, as we heard yesterday. The Unix philosophy which says, do one thing and do it well. And to really understand the Unix philosophy, I think it's instructive to spend an afternoon reading the man page for LS. So it's a beautiful angle on microservices, but it seems to me that the reason that microservices are dominant in the world and will be dominant for as far into the future as I can see has very little to do with purity and has everything to do with productivity, in particular, agility and flexibility for the release process, right? Like, if your release process can look like this so that different service teams can evolve and deploy different services independently because we've decoupled concerns and exposed explicit APIs, then site and product are going to be happy, right? You can go on releasing features, as opposed to a monolithic architecture where the release looks like the priming and a release of a pump or a waterfall, right? Ease of release is always going to win, and I think that there are so many benefits of microservices, but this is the one that's giving them the competitive edge right now. Now, but all joking aside, programmers love the model, because the model of microservices, much like the actor model in sort of programming language theory, allows programmers to focus all their attention on local correctness of the little people by shutting out the world, right? The world might be literally on fire around your service, but you can still make progress by using what this guy, Eddie Kohler, calls picture frame modularity. Like, it looks something like this. It's hot in here, but now I can focus on whether my service does exactly what it's supposed to. And then the hope, right? The hope is that if we get local correctness down, global correctness will follow by composition, right? Now, of course, microservices aren't as solipsistic as I made them sound just now. They need to know a little something about their neighborhood to be locally correct, right? Like, a microservice needs to know about the services upon which it depends. because it needs to be able to ameliorate unexpected returns from them and errors and so on. So you might think of a microservice as a white box that calls down into a couple gray boxes. And of course, if we're smart, we use all the best practices that we've read about. We put in the appropriate bulkheading and circuit breakers and things like this to make sure that the failure of one of our downstream dependencies doesn't pollute doesn't have other unexpected effects. And of course, we think very hard about the external API that we publish. If we understand that API, we understand a little bit about the services that might call us. Although to be fair, we should really say they're black boxes above us, right? We don't even know what they are necessarily in a highly dynamic architecture. Here's an anecdote that I can't tell you what company this is from, but I was consulting with a company, and there's an active project to mine logs and query them in Spark to determine the global transitive closure of the call graph at their site. Okay, let that sink in for a minute. There's this site that does stuff, they make money, and no one knows what the hell is going on. Somebody has to have like a tiger team of people to analyze logs to figure out what the fuck is going on, right? So, and this is really problematic for me because users don't interact with microservices, right? No microservice is an island. Users interact with sites, and they have sort of request-response interactions that light up a non-trivial subset of these services. Correctness from the point of view of a user interaction has very little to do with the SLA exposed by a particular service. It's really an end-to-end property. Similarly, fault tolerance or resilience of that interaction is an end-to-end property, a property that, as we've seen time and time again, doesn't hold necessarily under composition, even if we're lucky enough to build it out of all correct services, which is a big ask in such a dynamic world where services are evolving independently of each other, right? To reason about whether an interaction like the one I just showed you is tolerant to faults, to a first approximation, we would have to check for every combination of faults whether it still works. Well, that's not going to work, right? Because many service interactions that I work with involve 100 services. So there are 2 to the 100 things that could go wrong, right? Like if we're unambitious, we might just inject failures in one service at a time, and that's a space of 100. That might be tractable, but as we know, the juicy bugs happen when multiple things fail. Maybe different kinds of failures and different numbers of failures. And so if we turn the volume up to, well, what about up to 4 faults? That's 3 million executions. 7 faults? That's 16 billion executions. Like, this isn't going to work. We should stop here. Right? So to end this brief diatribe, the game of managing complexity is really 2 games: a checkers, deleting complexity, and a chess, moving complexity around. The second game is a zero-sum game that forces us to navigate a trade-off space. Very often, that trade-off space is a matter of productivity versus purity. And we always choose productivity. So what I'm going to argue at this turning point before I get into the sort of the technical material of the talk is, there's a silver lining on this cloud. Because in order to scale our infrastructure in an agile way, we've sacrificed to a large degree global visibility and confidence about resilience. A new class of tools and infrastructures is emerging in microservice-based organizations. And these tools are extremely powerful, and we're only beginning to scrape the surface of what can be done with them. So I want to talk about some of the opportunities from the point of view of a researcher, what we can do with these emerging infrastructures. Okay, what infrastructures? In order to address this big question of, what the hell is going on, call graph tracing systems are becoming mature, right? This was pioneered by Google's Dapper, but very quickly implemented at Twitter and open sourced in the system called Zipkin, right? Netflix uses heavily a Zipkin clone called Salp. Uber uses a Zipkin clone called Jaeger. Facebook uses a very similar system called the Mystery Machine. And because these are all converging to the same place and satisfying the same needs, an open standard is emerging called open tracing. I like to think that in a couple years, all large-scale companies struggling with these problems are going to have some clone of open tracing. So that's sort of our answer to the observability question. Give us a handle on what the hell is going on in our massive scale services. But in order to reason about whether they can tolerate faults, we need some sort of experimental infrastructure that allows us to test what happens under fault. This was an approach pioneered by Netflix, who incidentally inject all their faults in production because they're cowboys. But it was very quickly adopted by companies like LinkedIn, Microsoft, Uber, PagerDuty, and many others that I can't mention right now due to NDAs and friend-DAs and things like this. So we know how to break stuff, and we know how to see what happens. Isn't it tempting to try to fit these together somehow? Like if we could understand how our sites produce their good outcomes, maybe we could use that to drive the fault injection infrastructure to try to prune down that massive combinatorial space that I was just showing you. Well, in the current state of the art, we don't do anything that sophisticated. Like Chaos Monkey, the original fault injection, large-scale fault injection infrastructure, drove faults randomly. Essentially, it, if you like, throws darts randomly into this dartboard. Sometimes deep, sometimes shallow, and sometimes they get lucky and find a bug, right? Random search is great because it's fundamentally scalable. Right? You don't need to know anything about the architecture you're testing to do random search. So you get a new service, random search works just as well on any architecture. Unfortunately, it doesn't work very well on any of them, right? Like let's say there was a pin in that dartboard somewhere. What are the odds we're going to split that pin with one of these darts? And we can give up any hope of covering this dartboard black just by stabbing into it randomly, right? The sun will be burnt out before we're done with that. An emerging approach that I see much more popular more recently in the last couple of years is what I would call engineer-guided or heuristic search. The idea is that, in part due to Conway's law, engineering organizations are partitioned along the lines of their service architecture, right? So there are teams who are just experts in individual services. We can exploit their intuition and figure out what are the dark corners of that service. Think things like recovery paths and failover paths that have been insufficiently covered by unit and integration tests. We can force them into those places. And engineer-guided search ends up looking like this sort of guided walk through the space of failures, going sometimes deep, sometimes shallow, and achieving a good degree of coverage. But unfortunately, engineer-guided search is fundamentally unscalable and imperfect. It's only as good as the intuitions of the engineers, and it only scales with humans, right? Here's another anecdote. A colleague of mine was inaugurated as the chaos czar of an e-commerce company for which she worked, and she spent a bunch of time building a fault injection infrastructure, and when she was done, she was like, oh dear, now I have to run this thing. How should I run this thing? What are the interesting faults? And what she did was she took a couple months and set up meetings with service teams and walked around and sort of assembled in her head the union of all this local knowledge. The information that would be in the head of like a chief architect if there was such a thing anymore, right? And of course, she could be hit by a bus. This is not a scalable approach either. So obviously what we'd like is for there to be a puzzle piece that fit in between these two things, right? Something that could understand how the site does what it does and use that understanding to drive the search through faults. Something like a cunning, malevolent sentience. But none of us want to wait around for strong AI. So in the meantime, I'd like to suggest a middle ground, an approach that my colleagues and I call lineage-driven fault injection, or LDFI. LDFI was first proposed in SIGMOD, which is a database conference in 2015. At a really high level, the idea is that fault tolerance is really just redundancy, right? Fault tolerance and redundancy are sort of synonyms, if you think about it for a minute. A system is fault tolerant if it provides more ways of getting to a good or expected outcome than we anticipate there will be failures. Let me give you some examples. Like, to guard against component failure, we replicate, right? That's sort of redundancy in the dimension of space. To guard against message loss, we use timeout and retry. That's redundancy in time. Databases make themselves recoverable by storing 2 copies of the data of record in the data pages and in the write-ahead log. Redundancy and representation. ECC in memory, or error-correcting codes in memory, or mathematical redundancy. K-version programming is redundancy in the program text itself. I challenge you to to share with me a fault tolerance strategy that does not involve redundancy in some form if you sort of zoom up high enough. And so if we could identify the implicit redundancy in a system, if we could identify all the alternative ways that a large-scale fault-tolerant system provides resiliency, we could understand what faults it could tolerate, or conversely, we could understand what faults could break it. But how do we know redundancy when we see it? So the other key insight behind LDFI is to say, instead of thinking in a forward direction, saying, how could a bad thing ever happen, right? That's like what a model checker does. It has some initial states and a transition relation, and it takes all the transitions, and it says, all of the states that are reachable are good. That's a great approach if it's a tractable space of states. But if it isn't, it doesn't give us very much guidance about how to carry out the search. So LDFI says, no. What you should do is you should work backward from good outcomes. You should ask, why did some good thing happen? And could you have made any wrong turns along the way? So the answers to those questions are going to turn out to be the faults that are interesting and worthwhile to spend time and resources injecting with our experimental infrastructures. Let's make this conversation a little bit more concrete and consider a lineage graph, a structure that encodes redundancy that we can extract from computations. So let's imagine we had a storage system like Cassandra. A good outcome of an interaction with Cassandra might be like, well, the client made a write and it got acknowledged and the write was stable. It was durably stored. That's the good outcome. So we ask, okay, Lineage, why was the write stable? Well, it's going to turn out that the write is stable because it was stored on some replica A. But it was stable for more than one reason. It was also stored on replica B. So we have some explicit evidence of the system's implicit redundancy. Say, well, okay, but why was it stored on replica A? This is a recursive process of asking questions. Well, sir, it was stored on replica A because the client made a broadcast. But it was also stored on replica A because the client made 2 redundant broadcasts. Now the game becomes, the game of how could we prevent this good thing from happening becomes, can I devise a set of cuts that breaks the flow, right? So what are all the things that could go wrong? Either the replicas could fail, and either the broadcast could fail, so that's 2 to the 4, 16 possible combinations of failures. But a quick perusal of this graph tells us that they're not all interesting, right? For example, this cut is not interesting because there's still a path to the good thing. It would be a waste of time to go inject that fault. By contrast, this fault looks promising, right? It blocks the flow. We'd like to see what our system does in the event that these 2 broadcasts are interrupted. Now, to turn this into something that a computer can solve rather than a person with intuition, we need to encode this structure symbolically. And that goes something like this. We're going to mine out all of the individual paths to the good outcome, paths that are in themselves sufficient for the good outcome, and reason about how we would break each path. Now, each path required all of its component pieces, so we can kind of write down, well, to break this path that I've highlighted, we could crash replica A or interrupt broadcast 1, right? But wait, here's another path that isn't itself sufficient. Well, to break both of them, we would have to crash replica A or broadcast 1 and replica A or broadcast 2. So we just we turn the crank, we mine out the paths, and as we do so, we cons up this, what you may recognize as a positive Boolean formula in conjunctive normal form, a formula that we can readily ship off to a state-of-the-art satisfiability solver and let that thing do the heavy lifting. The solutions to this formula are going to represent the sets of faults that are interesting to go explore according to our current model of the system's redundancy. So for example, the solver might say, broadcast 1 and broadcast 2. We say, great. We parameterize our fault injection service, inject those faults. We're not done yet, right? Because we're assuming that this is a fault-tolerant system. Fault-tolerant systems might have more redundancy than we see. Okay, so in the event that we crash both these broadcasts, we shouldn't be surprised to see the system time out and broadcast again. And that's okay. That's okay, because now we can enrich our model of the system's redundancy, and next time we come up with a hypothesis, it will be smarter. Okay? What we want, and what indeed we get from LDFI is 2 things. The first is that instead of casting darts randomly at this dartboard, we're throwing them into regions that we can prove, according to our current best model, could break that expected outcome. And even more importantly than that, when we cast a dart into the dartboard, it casts a shadow over the search space, and there's a region that we never need to throw a dart into again. Okay? So at a really high level, LDFI works in the following way. We begin with a successful outcome, something good that happened, and we ask, okay, well, why? Why did it happen? This recursive process of asking and answering why questions yields a lineage graph similar to, but obviously much deeper and more complicated than the one I just showed you. We can encode that lineage graph in a very straightforward way into a positive Boolean formula in conjunctive normal form and call out to a satisfiability solver. The solutions to that formula are going to represent interesting faults that we can now harness our fault injection infrastructure to test. And then one of two things happens. We find a bug, in which case victory or defeat, depends on how you look at it. But LDFI's job is done, right? Or the system reveals additional redundancy, which we can use to enrich our models and make better suggestions next time. So, some of you might be thinking, I'd like to buy your product. The good news is you don't have to buy it. You can build it yourself because you have the basic requirements, or if you don't have them, you will have them when you start having these problems, okay? So what you need in order to implement LDFI at your site, like we've done at Netflix and at Uber, is is a fine-grained fault injection infrastructure. The finer grained, the better, but you can make do with surprisingly little. Some mechanism for collecting lineage, and in my experience, perhaps surprisingly, call graph-based tracing is a reasonable substitute for lineage. And I'll talk a little bit more about that in a couple slides. And finally, as you saw, we go around this loop some number of times, we require the ability to replay interactions. Now, how difficult this is going to depend very much on your site architecture. If you have a large-scale staging area, then replay is cheap. If you're cowboys who do all your fault injection in production, simulating replay can be non-trivial. And so if you're interested in the solutions that we came up with to that problem at Netflix, I encourage you to watch my QCon London keynote that I gave with my colleague Colton Andrus, where we dig in and talk about how we approximated replay in a highly dynamic world where we're injecting faults in production, and the only interactions that are happening are live user interactions. That's a fun talk. Some of you with some familiarity with call graph tracing infrastructures may be scratching your heads now and saying, wait a minute. You showed me a lineage graph that had all this redundancy, and you use that redundancy to reason about how to prune the space of failures, but a call graph doesn't reveal redundancy, right? It just says what happened for a particular request response. Like here's a very small call graph from Netflix that, a user came in, it hit the API tier, and it collected some bookmarks and rating information. You say, well, that doesn't tell me, for example, that get bookmark has a fallback. I mean, certainly it does, right? This is Netflix. They're highly fault tolerant. But the redundancy is implicit in the site. It's not explicitly revealed in the call graphs. Well, it's just a matter of waiting. So if we come up with a hypothesis that tells us we should fail this service, and we fail it, what ends up happening is Netflix produces a new call graph that reveals the fallback path. If we take the union of these graphs, we begin to approximate something that looked like the graph I showed you earlier. We begin to have an explicit representation of otherwise implicit redundancy by forcing the system into these dark corners. And over time, this merged graph ends up being a model of all the alternatives that the site can produce. Now some of you might be thinking, that's cute, does it work? Let me dive in on one data point for this. We did a deep dive at Netflix on an interaction that the engineers there colloquially call app boot. It's sort of the set of calls that are necessary to prime a device and get it ready to begin streaming. So authentication, DRM, collecting the bookmarks, recommendations, all this kind of stuff. It's like a moment of truth for Netflix, because if that doesn't work, their users are gonna go to Amazon, right? It involves about 100 services. So in order to test it exhaustively, we'd have to search a search space of 2 to the 100 executions. That's like a 1 with 30 zeros after it. And we deployed this last summer and ran it for a few days, and it covered the entire space in 200 executions, finding along the way 11 critical user-facing bugs and what everyone had thought was a profoundly well-covered execution path. That was cool. So to sort of begin to wrap up, I'd like to share some fairy tales with you about the future. What are the basic requirements for first-class distributed systems R&D for massive scale systems? I think we need to answer this if we're gonna make any progress, right? It seems to me that there's 4 basic requirements, and the sad story is that there is no place on Earth where all 4 of these requirements are met. Now, obviously, any academic will tell you the first thing we need is real problems. Like, what are the pain points felt by practitioners and their customers? Because academics are creative people, and in the absence of knowledge of real problems, we're perfectly happy to invent fake problems and solve them and write papers about it and cite each other, and but that doesn't really move the needle, right? And it certainly doesn't have any impact. I think even if we're lucky enough to have real problems, like maybe we come down from the ivory tower every now and then and have beers with our industry friends and ask them what really sucks about their job and get a better model of real problems, we're not gonna be able to make much progress without real systems, because people, this is distributed systems, right? Like, we can't test the fit of our solutions without scale, without the computers, without the workloads, without the users, without the infrastructures, Sure, we spend a lot of time simulating large-scale distributed systems, but that isn't how it should be done. So we need real problems and we need real systems. And if that was all you needed to do first-class distributed systems R&D, go forth. But it seems to me you need more than that. You need time, like a lot of time, because sometimes greenfield, blue sky stuff, it takes order of a year, 2 years to have an idea and prove it out before you have any results. Like, imagine telling your boss, I have this great idea. It's going to improve site resiliency. I think it's going to give us another 9 of availability, but it's going to take me a year to have any results. Can I do that? How many of you think you could do that? Okay. Now, imagine this. Imagine if you said, oh, there's one other thing. At the end of that year, I might have to say, yeah, it didn't work. Sorry, can I have another year to do a different thing? So great research requires time to think and, more importantly, freedom to fail, right? And that's what the academic system is all about, right? That's what education is all about. It's okay to be wrong. Unfortunately, this is kind of what the world looks like right now, right? We can grow things in these pots, but not the things we want to grow. They're unlikely to bear fruit. One thing has water, right? One thing has sun. And so, okay, what do I think we should be doing? I don't know. I'm just one person. But I do have the bully pulpit, so I can talk a little bit about what's worked for me. I'll tell you what hasn't worked. Year in, year out, I've seen throw it over the wall attitudes in both directions failing to provide to bridge the gap between academia and industry, right? Let me give you one example of throw it over the wall. Colleagues in industry often will say, well, write some production quality code and open source it and we'll try it out. Yeah, well, you're going to be waiting a long time for that. Obviously, first of all, academics aren't the best at writing production code. Second of all, without the knowledge of the real problems and without the systems to test it in, we're going to build the wrong software and you're not going to use it and nobody's going to be happy. Another version of throwing it over the wall logic is academics saying, well, if our industry partners would just give us a data dump, then we could figure stuff out. We could put a bunch of grad students on it. I've never, in my almost 9 years now of being in academia, seen an industry partner share a data dump. And this is for good reasons, right? There might be personally identifiable information in it. There might be trade secrets hidden in it. But even if they did throw a data dump over the wall, academics aren't going to know what to do with that thing. Forget throw it over the wall. You know what's worked for me and my colleagues? Deep embeddings. Like what I was saying about spending 3 months every year, ass in seat, immersed in the culture of a company, feeling their problems, and as painful as it was at first, following their processes, like participating in internal RFCs, committing code to the real repo, Like the thing where you write the academic prototype and then you're like, port this thing. Like, that never works, right? Write production code and, go through code reviews. Deep embeddings where you sit next to your colleagues day in, day out. And then the other thing that works is, I kind of already started to talk about it, is kind of, walking for a mile in each other's shoes. Like, I think academics have a lot to gain from the sort of rigor that is expected in industry. And I think, at least in my experience, industry practitioners are really academic curious. They're more than happy to participate to the extent it's possible in blue sky research, to collaborate in paper writing and dissemination. For example, my colleagues at Netflix are all co-authors in a paper that we just got accepted at ACM's Symposium on Cloud Computing. My colleague Colton, who's now at Gremlin, my colleagues Chris Sandin, Casey Rosenthal, Ali Basiri, and Lauren Hochstein at Netflix. Today, probably concurrently with this talk, my colleague Colton is at the ACM Symposium presenting for a completely academic audience the fruits of our work at Netflix, while I'm here trying to sell these ideas to an industrial audience. So, go dig deep, maintain the relationships for a long time, switch shoes. There's so many opportunities for growth. And so I hope, regarding throwing things over the wall, one thing that is good to throw over the wall is money, because because grad students are hungry. That works. But nothing else works going over the wall. So I would like to work with you all in whatever capacity works for both of us. And here's a little taste of some of the projects that I want to get started on. So I have a great team, 3 exceptional grad students, 2 amazing master's students, and a small army of undergrads chomping at the bit. So I'm going to have to go fast because I'm running out of time. But so 3 areas that I want to work on are search prioritization, input generation, and improved collection of lineage beyond call graphs. I'll spend about a slide on each of them before I close. So as you saw sort of in the middle of the talk, we constructed, by walking the lineage graph, this Boolean formula in conjunctive normal form. We passed it to a SAT solver. We essentially posed the problem of finding faults as a decision problem. Does this have a solution, and what is it? Now, as I learned at Netflix, when our lineage data is of coarse grain or poor quality, as is the case with call graphs, the space of solutions itself can be very large, too large maybe to explore exhaustively. What we really want is some kind of ordering of the space of solutions that captures likelihood, right? Next time we harness our fault injection infrastructure, we should be exploring a fault that is not only possible according to our model, but also likely, okay? So one sort of first step in that direction is to say, instead of posing this as a decision problem, we should pose it as an optimization problem, something that finds the best solution. So we can convert this positive Boolean formula into just a set of sets with the same variables. And really the problem that we have at hand is there a set of faults that hits each of those sets and that has the property that it is the smallest such set of faults, right? So for example, this is a well-known problem, the minimal hitting set problem, NP-hard problem, unfortunately, but CEH hits every one of those sets at least once, and there is no set that hits all the sets that has only 2 or fewer elements in it, right? Of course, this approach, which is quite sweet, I think, makes some simplifying assumptions. It assumes that all faults are equally likely, which is horseshit. It also assumes that all faults are independent, which is also horseshit. For example, imagine if I had these 2 different models of redundancy of these 2 different good outcomes. It would appear to a first approximation that the one on the left is more resilient, because to break it, you would have to break 3 things rather than 2, right? But that wouldn't be true if I knew something about the containment hierarchy that said that those 3 were in one failure domain and the 2 were spread out across 2. And in fact, this nesting of failure domains, as I'm sure you're all aware, goes quite deep. Right? Like I could have, let's imagine that this is like a replicated storage system, and you have these 2 durable outcomes, each of which depends on 3 replicas. They both appear equivalent. unless we were to learn that one was spread across 3 racks, and one was on 1 rack, and one was spread across 2 data centers. And so really what we need is to enrich our optimization problem and not just measure the cardinality of this hitting set, but try to maximize likelihood, given some probability distribution over the relative likelihoods of nodes, racks, data centers, top of rack switches, power supplies, and so on failing, and the containment hierarchy, what's in what. Okay, oh my gosh, I'm almost out of time. So a really important problem in LDFI, and a problem that we've swept under the rug, is input generation. In the early days of LDFI, I sort of glibly argued that the problem of searching the space of inputs for bugs is completely orthogonal to searching the space of faults. And so I said LDFI is complementary to fuzz testing, and property-based testing like quick check, model finding, blah, blah, blah. Now, of course, that's not true, because some of the most juicy bugs involve intricate combinations of input events and failure events. One of the most famous that comes to mind is Pamela Zave's debunking of the Chord protocol. Chord was an early distributed hash table developed at MIT. It won best paper at SOSP. It had all these great proofs of its correctness. One of the most important correctness properties that they proved was that this consistent hashing ring can never be split into 2 rings. Because if that were to happen, the rings would never heal. We would have a permanent split brain. So that they proved this with words. And then Zave disproved it with an actual counterexample. She said, well, here's an execution in which there's 2 nodes in a ring. Along come 2 other nodes, and they join the ring, and the successor pointers are updated. But just after the successor pointers are updated and before the successor of my successor pointers are updated, those 2 nodes crash. And we're left forever in a split brain. This is a fascinating example for me, because first of all, don't believe anything you read in an academic paper, except for mine. And second, LDFI would never have found this, because it involved carefully interleaving and co-optimizing the search through failures and inputs. I have a great grad student who wants to work on this. We need real systems and real problems, and your input. I don't even have much of a slide about this, but the holy grail for database researchers is better collection of lineage or provenance or explanations. I'm extremely pleased with how far we were able to go with the relatively impoverished lineage that we get from call graphs. But between these 2 extremes of call graphs and pure data provenance is a wide space that I think we should explore. And this introduces really challenging engineering problems as well as research problems, because with tracing, the game isn't just figuring out how to collect the data. It's how to collect the data without imposing unacceptable overheads. Okay, so I like to think that this is pretty much where we are right now. We know how to break stuff. We know how to reason about what happened. The industry leaders are here now, and everyone will be here when they have these problems. But where I think we're headed, hopefully in a year or 2, is snapping things together and using lineage-driven fault injection or similar techniques to build models of how a system provides alternative ways to achieve its good outcomes, how a system makes itself fault tolerant, and use that to drive our search through failures. So I couldn't have done this work without my host institution, Santa Cruz and Berkeley, my collaborators, Netflix, Uber, Elasticsearch, and Gremlin. Thanks very much.